Hello friends, welcome back to another video. So in this video, I'd like to discuss the Euler-Lagrange equations again and the variation principle, obtained in a more rigorous way, but still not the most rigorous way. Leave that for another video. And since we've already done it for the case of classical mechanics, I thought maybe this time we could do it for field theory. So I already wrote what our action is in the field theory. So it's a four-dimensional integral over something called a Lagrangian density. It's going to be a function of the field phi and of all the derivatives. So when I write this del phi, it means del 0 phi, del 1 phi. Maybe here I'll write transposed. Del 2 phi, del 3 phi. And it's like a form, right? So it will have lower indices, whereas x will have upper indices. Okay, and now I want to introduce something that's called a one-parametric group of symmetries. So one-parametric group of continuous symmetries. So if we have this field phi, I'm going to write uppercase phi, depending on this variable s in R. So for all s in R, I define this phi of s, which will take our field, and yeah, it will be a function of the field. Okay, it'll be a function of the field, and it will depend on s continuously. So what I mean by that is I can differentiate it. So also a property is that f of 0 of phi is phi, and phi s of phi t of phi, although we're not going to need this property, is phi s plus t of phi. And so you can deduce from this the inverse. So phi minus s is phi s inverse. Okay, and this phi is, well, this is the role it's playing. So let's imagine just the coordinates, right? Imagine that we're back in classical mechanics and phi is just q. Big phi s is then q s of q. So I depict something like q of t. That's a trajectory. And then a trajectory phi of s might be something like that. Phi of s. It's continuous with s would mean that maybe like phi of s plus delta s, like a small increment, would be like that. So if I differentiate, they keep, you know, and this condition, yes, I didn't write this condition yet. So phi, so if this integral, in field theory, this integral is usually over R4. So you'd need that at the boundaries, but that's at R4, phi s matches phi. In this case, the one that I drew, oh sorry, these should be q. So in the thing that I wrote here, if this is b and this is a, then you'd have qs of a equals q at a, and qs of b equals small q at b. Yeah, I should write qs at q of a, qs at q of b. Okay, yeah, no, it was right. This was right, but then this is a, and this is b. Yeah. well, yeah, you know what I mean. That these ABs are vectors technically. Or maybe this is time and no, yeah, this is not gonna work. The drawing is not made for this, so this vector can be B. This vector can be A, or other way around. Okay. Yeah. Okay. And now just generalize that to a field, because I can't really draw a field. At least it would take too much time. And now I want to look at what S, phi S would be of phi. It's just this integral. I'm not going to write the integration limits. The integral of phi S of phi, the derivatives of phi S of phi, and maybe x dx. And now I just want to minimize the action, right? I want to minimize the action, and what I have is I have these different trajectories, so I want to find small phi for which it's minimal. So phi will minimize S if d phi S by ds, sorry, if ds, because you see the action itself now depends on S, small s, continuously. So if this at 0 is 0, and why do I say at 0? Well, because at 0, phi 0 is equal to phi. So now I just take the derivative. And this is just a chain rule, right? So the first argument will be this. And so let me just write the first derivative of the Lagrangian. So derivative of the first component I will write as del lambda by del phi. Okay, here I'm just like implying that this is where phi is normally, this is where del phi is normally, but you know, the chain rule is just like find the first derivative with respect to the first argument. It doesn't matter which symbol you put. So that's what I'm meaning by this notation. And then the second one, so here we have del of, now I'm going to write this explicitly, so we have components. And then dl by del mu phi. This is just a way, obviously, for me to, here there's an implied sum, right? Einstein notation. But this is just a way for me to write that L is actually L of phi, d0 phi, d1 phi, d2 phi, d3 phi, x, and then obviously dl will be a vector. So if I write d mu l, it will be a derivative with respect to one of these, right? Depending on what mu is. Is mu 0, is mu 1, is mu 2, is mu 3. So if I just want to sum over all of them, I write like this. Because we do need derivatives of all of them. Okay, and maybe I just put this a bit to the left. So the x is just integrated over, it's a coordinate. It does not get affected by this variation, by this s. So I don't need to differentiate the last argument. Maybe I put dx here to save space. Okay, and now you can recognize that obviously this derivative will commute with partial mu. So I'll let me just copy paste this and then commute them. So here there is like this, and then partial mu, just making sure that it's like this. And so now we'll partially integrate this term. So these integrals are always 0 at the boundary. In this particular case, we require fields. So fields at x mu equals minus infinity is 0. There's no field at spatial infinity. So that part's kind of simple. The boundary term will die. So we'll only get minus d phi s phi ds d mu del L del mu phi. And boy, does this look like an Euler-Lagrange equation, doesn't it? Now notice that these L's are obviously still functions of phi s, big phi s, of the one parametric group of transformations. But now we apply the condition that at s equals 0, this needs to be 0. So we have ds phi s phi ds at s equals 0. We require it to be 0, and that's we apply this evaluation inside, and notice that I can group these two terms together. So I write this like this, taking the derivative and then taking s equals 0. Obviously those two operations don't commute, but what's on the factorized part is dl by d phi minus d mu dl d mu phi. And now these L's are functions of phi's. The evaluation went through. So we have that this is 0, but you see these phi s's, I only have a constraint on where they begin, where they end. And I have a constraint on what happens is if s is equal to 0. So again, on this example where phi's are just coordinates, this is what I have fixed for phi, and then maybe this is what I have fixed for phi s, right? For any given small phi, this is what I have fixed for phi s, for s equals 0. This is s equals 0, and this is phi equals a, this is phi equals b. So everything else is unconstrained. I could have anything else. So the derivative, you see, if for example this was for s equals t, the derivative would be, or maybe like s equals delta s, like small increment. The derivative would be like that. But if this is s equals delta s, the derivative would be like this. So I really don't have any constraint for the derivative, and I don't even have a constraint, I don't need to raise this, and I don't have any constraint on big phi. So phi is unconstrained. It's any function that's continuous in s, right? So if I have this integral, and notice that the left-hand side, well, it does have phi dependence, but yeah, if phi is unconstrained, it could be any function, so the derivative doesn't have to be 0. So it's this that has to be 0. Now I know this is a bit hand-wavy. The next video is going to be even less, like it's going to be no hand-waving at all. But this is already pretty rigorous. So yeah, so therefore it's this part that has to be 0. I'll just copy paste it. And these are the Euler-Lagrange equations. Euler-Lagrange equations. Yeah, for fields. Phi. And yeah, so of course here I have phi d phi x. And you can write that here as well. Maybe I'll give a small example. So suppose L is d mu phi plus phi squared 1/2. Okay, so then d L by d phi is, so we should write it, yeah, it's just phi. And then dl by d mu phi. Okay, now this, like, be careful here. It's best to, because these are dummy indices, right? They're being summed over. So you can write 1/2 dl. So okay, d mu phi, right? Let's write mu by d mu phi. So you notice that this guy and this guy will cancel if you have that mu is equal to nu. So that's 1/2 d nu phi, copy this part, that's what remains, right? Times delta nu mu. Okay, and then it's this term left, so plus 1/2. Usually you would never do it this slowly. Plus, so I copy this term, and then I have, yeah, sorry, I forgot this delta here. Delta of delta nu phi, delta mu phi, but this guy is equal to eta nu sigma d sigma phi, and this eta is just the Minkowski metric, right? This is just the one. I'm going to use this signature. Okay, so obviously it doesn't get hit by the derivative because it's just full of constants. And then this and this cancels if sigma is mu. So it's 1/2. I'm going to apply the delta function here. So it's delta mu phi. And then plus 1/2. So we have delta nu phi, eta nu sigma, and then delta mu sigma. So mu is replaced with sigma, delta mu phi, plus, so nu is replaced with sigma, sigma is replaced with mu, and then nu is replaced with mu, but raised, and that's d mu phi. Okay, that's a bit too complicated. I just wanted to show it how it works, but yeah, obviously you know it's this. Yeah, and so from the Euler-Lagrange equations, let's just copy this. Yeah, forgot to add the 0 there. So we have that phi minus d mu phi is 0, or rather, there should probably be a minus here. I'm gonna change this to minus, so this is minus, so that this is plus. So this means that phi double dot minus, this is, yeah, okay, Laplacian phi plus phi equals 0, where this Laplacian is dx squared plus dy squared plus dz squared. Okay, and this is called the Klein-Gordon equation. Sometimes you'll see it written like this as well. Nabla phi plus phi equals 0. There should be a mass as well, probably, but who cares? Set mass equal 1. Okay, yeah, this is a small example. Mainly I just wanted to show how these derivatives work. Yeah, okay, that's it. Hope you guys liked it. you next time.